Hello everyone and welcome to another wonderful day of physical chemistry. So today we're going to go ahead and take a step back and revisit our orbital energies. So now we've got a good idea of how we can build an electronic orbital. Now we need to try and figure out, well, which orbitals are we going to fill up first? S, P, D, let's be honest, why? So one of the things that we're going to really try and do is figure out the relative energies of each orbitals in a multi-electron system. And we've already just built up a decent model for this, and that was our good old friend Z effective, or essentially how much nuclear charge our electron effectively feels. So this can be thought of as the nucleus has a certain amount of charge, and then we're essentially subtracting out a term that gives us more or less electronic repulsion, but also can be thought of as electrons standing in the way of the nucleus, getting in the way, and thus is often referred to as the shielding constant. So more or less, the closer I am to the nucleus, what we're going to find is we're going to have a lower shielding constant because most of the electron density is going to be on the outside and is going to push me towards the nucleus where I'm happy to be. But when we get far away from the nucleus, now I've got this extra repulsion, which is going to give an additional shielding of the nucleus. So what we're really going to be focusing in on is how many electrons are there closer to the nucleus than me that are pushing me out of the way. Now, we've seen before, we have this general idea, closer electron comes nucleus, better it is able to essentially get around this effective shielding of other electrons. And this is where the influence of the angular momentum becomes really important. Because if I take two orbitals, say the S and P orbital, equivalent quantum numbers, what we tend to find is that while the S orbital is on average further away, it has these extra nodes of increased electron density near the nucleus, which gives the S orbital a competitive advantage over the P and D orbitals. And we're going to see a similar thing. It gives the P orbitals a little bit of a competitive advantage over the D orbitals. So in general, what we tend to find is that even though as our angular momentum increases, we on average get closer, we also have less penetration of the electron shielding of the core electrons. So kind of paradoxically, the larger the the lower the angular the momentum, the more penetration I get, and thus the more stable the system gets. So often what we're going to find is that the electron with the greatest penetration is going to give me the highest Z effective. So for example, if I'm looking at carbon, the 1s orbital has much higher Z effective than the 2s, which has higher Z effective than the 2p. And so we're going to tend to see a general trend. What we're going to find is that our orbitals with a higher penetration are going to give us lower energies. Just think of our good old friend, the modified Rydberg for a Z effective, as the energy should roughly scale as Z effective squared. Negative Z effective squared, giving the 2s a much lower energy than the 2p. And in general, we can order our subshells as S is more favorable than P, is more favorable than D, is more favorable than F. So what we're going to do over the next couple lectures is look at how these orbital energies can help us figure out orbital filling patterns and thus the interactions of a poly-electron atom. Until next time, take care.